So now that we're aware what an addition reaction is, let's look at some specific types of addition reactions. So the first mentioned in section 8.5 is this hydrohalogenation. So as the name implies, we're going to add a hydrogen and then we're going to add a halogen across our double bond. This can be accomplished using either HCl, HBr, or HI. We will not see HF, so no HF across our double bond. So when we have our addition reaction here, we might consider which of our vinylic positions, right, which of these two spots will add our hydrogen or our halogen. Where does X go, right? If we have an asymmetrical, a not symmetrical alkene, we have to consider this, right? We might get a different response or a different result than we're expecting. So we see up top here, right, we have this symmetrical alkene, and we don't really have to consider that. We know that either side here will end up with the same final product. And we see that at very low temperature, negative 30 degrees Celsius, we get about 76% yield of our product. So let's look at what position will the H be installed and which position will our X, our general symbol that's used for chlorine, bromine, or iodine. So we have two vinylic positions. We have our asymmetrical alkene here, and the radioselectivity, the region that will be selected with the bromine will be under Markovnikov addition. So if you recall, Markovnikov addition has to do with the more highly substituted position, gaining the bromine. We can also look at it as hydrogen atoms tend to flock to where there's more hydrogen atoms already present. So when we compare our asymmetrical alkene here, the one side, right, there's a hydrogen, so the hydrogen will go there, and then the other side, we would install the bromine. So that's what we see here in our product. We see hydrogens go where hydrogens already are, and the bromine goes to the more substituted position, right? So more substituted gets the bromine, gets the halogen. Now that is not the case, right? We see the opposite radioselectivity observed when we have a peroxide present. So this organic peroxide causes us to see an anti-Markovnikov addition. So if we had to choose, right, this side has more hydrogens here, but we can see in our product that it gains the bromine on that side. So anti-Markovnikov addition when we have a peroxide present. So this we can see, right, the important point being made here is that we can control the addition of a halogen, specifically HBr, with our alkene here, depending on whether or not a peroxide is utilized. So we see again Markovnikov addition, the more substituted side of the double bond. In this case, we'll get the bromine, and then the anti-Markovnikov addition, where the hydrogens are, now the bromine gains there, right? So the least substituted vinylic position. So we can work through here and figure out what would our expected major product be, because we know that there's always going to be minor products as well that do not follow what we expect at times. So for our first example here, we'll call this example 1, we see that we add HBr across the double bond, and there's no peroxide. And then in example 2 here, we're going to add to our asymmetric alkene, again, HBr, but with the presence of peroxide. So let's look at the differences here, right? So we have our vinylic positions to choose from, right? Both of these are vinyl positions, and we want to know which will add the bromine, which will add the hydrogen. So we have Markovnikov addition expected here, and then anti-Markovnikov down here. So with the Markovnikov addition, we look for the more highly substituted position, and that's where we see the bromine has added. Down here, we look for the least highly substituted position, and that's where the bromine has added here. So we'll go through some additional problems in the textbook, but in the meantime, let's take a look here with the mechanism. So we're always going to see a two-step process with this hydrohalogenation mechanism. First step, the double bond here performs a proton transfer or grabs a proton, right? Those electrons within the bond move to the bromine. The bromide ion that results, in addition to our carbocation here, so we have two products that result, right? So we break the double bond, we protonate the double bond, and then we end up with this tertiary carbocation. And then we have our second step, the nucleophilic attack. Both of these steps we can see are reversible. This slide here is kind of showing us a deeper view as far as the thermodynamics and the potential energy of each of our steps shown here. So we need some activation energy to reach this proton transfer step. And we see that the formation of our carbocation intermediate would be our rate determining step, right? So if you're ever asked about which step is the rate determining step, the one that requires higher energy of activation would be our longer step, right? So that would determine our rate. And we see our nucleophilic attack, and then our final product with this lower potential energy. So again, just to review, when we have Markovnikov and anti-Markovnikov products, we can base these on carbocation stability. So remember, there could always be rearrangements that occur, and carbocation stability is key when we look at our potential products. So this graph here is comparing the potential energies of a secondary to a tertiary carbocation, and you can see that the tertiary is a lower potential energy, and this would be a faster reaction, right? So that is the why, right, or the how, I guess, behind these Markovnikov products forming. It's because the intermediate, the carbocation, the tertiary carbocation specifically, is at a lower potential energy, so therefore that would form faster. When we talked about the regiochemistry already, but the stereochemistry, that has to do with when we create a chiral center, whether or not we designate the configuration as either R or S, right? So we have two Markovnikov products, right? So two equally valid products. And we know that when we create these chiral centers that we're going to have two enantiomers in equal amounts, right? So there's no enantiomeric excess that would be produced. And this really has to do with the fact that we have a planar carbocation intermediate, right? So it's kind of flat here, this tertiary carbocation. So that's what we see in this plane here. And the sites of attack, right? So either from the top or the bottom of the plane will result in either a R or S configuration, but either side of the plane, either side of the carbocation can equally be attacked. So we would end up with an equal mix of the two products. I mentioned this before as far as rearrangements that can occur. So we can either see movement of a hydrogen or a hydride shift or a methyl group, a CH3, right? So a methyl shift can occur. And if they will occur, right, if our secondary carbocation can shift to become a tertiary, assume that it will occur, right? So if they can undergo rearrangement to a more stable tertiary, they will, and that is how you can predict your final product. So we can see here with this, right, when they can occur, they do occur. So we have our unsymmetric alkene, and we see that the secondary carbocation site is only about 40% of product, whereas the tertiary site would be a 60% yield. So when a carbocation rearrangement can occur, it will occur. So this is the end of this tutorial. We'll continue next time with section 8.6.